Today I will show you how to extend the classical Newton method to a wider class of non-differentiable functions. This will be done in the context of constraint optimization problems. So this video is twofold. In the first part I will show you how to reformulate an optimization problem into finding the roots of a non-smooth functions. And in the second part I will show you how to find the root of this function. Hi, my name is Frank and welcome on my channel. Let's start with the following result for unconstrained optimization. This is very well known, I'm pretty sure you know this. Assume that we have a differentiable function going from R to R. Then we know that a solution x star to the following optimization problem, minimizing f of x over the whole domain, must satisfy the first order optimality conditions, which reads as f prime applied to x star is 0. And how do you find such points? How do you find the roots of f prime? Well, just apply, if we have a twice differential function, just apply Newton's method. Well, Newton's method, you can see it here. We assume that we have a twice differentiable function. To finding the roots of f prime, we apply Newton, so start with an arbitrary point given and compute the following expression. I mean, this is pretty standard, this is well known. We can prove convergence speed, we can prove convergence, at least local convergence, and stuff like that. This even can be extended to function spaces, which is a very well known and well understood method. However, how can we apply this method if we have box constraints? So assume that we have so-called box constraints. So we want to minimize, again, we want to minimize f of x, but now we have the additional constraint that x must be in the range of a and b. So a must be less or equal than x and must be less or equal than b. In this case, the first order optimality conditions we just saw, reading f prime of x must be 0, is not a necessary or even a close a sufficient condition. Consider the following example. Assume f of x is just the identity, a is -1 and b is 1. The obvious solution for this optimization problem here is just x star is -1. However, f prime applied to x star is always 1, so it's never 0. So our first order optimality conditions in the unconstrained case do not hold in the constrained case. And here is the solution to our problem. This, I think, is one of the first results you will see when you visit a lecture about optimization 1 or something like this. Here you can see again our constraint optimization problem. In red, again marked, are the box constraints. And now we know that if x star is a solution to this constraint optimization problem, it must satisfy the following condition here. So this reads f prime x star multiplied by x minus x star must be greater or equal than 0. And this must hold true for all a and b. If you're a little bit more advanced, you will notice that this looks like a directional derivative, and this in fact that's all it is. F prime x star multiplied by x minus x star can be or is the directional derivative in the direction x minus x star, and this must hold true for all so-called feasible directions, so the point inside the set a and b. However, we will now just prove this. This is a very easy result to prove. So here's the proof. We assume that the result is wrong. So we assume that there is a p lying inside the interval a and b, such that the directional derivative inside direction p minus x star is less than 0. This, of course, shows if this product is negative, we know that both component must be non-negative. So the f prime x star must be not 0. Define h as the direction p minus x star. Now we know, now we use the continuity of f and f prime to get a delta hat such that for all delta which lie between 0 and delta hat satisfy the following condition. So f prime applied to x star plus delta times h must have the same sign as f prime x star and must also be non-negative. Why are we using such a thing? Because we now can simply use Taylor expansion and we know that we assume that we get a bar delta to get our rest term handled here. So we want to tailor f of p. So f of p is just fx star plus h. Just put it in here and you see this is true. And now we tailor. So fx star plus h is just fx star plus our rest term. But by our construction, we know that this product here is negative. So this means that f of p is actually less, not less or equal, it is less than f of x star. And again, and of course, this is of course a contradiction to the optimality of x star. So here you can see again our theorem, which just proved. As I told you, of course, this can be put into a more general setting. The condition you can see here actually is a special case of a so-called variational inequality. If you're interested in, just fire up Google and put variational inequality in it and you will get a lot of results. And again, this result, of course, can be embedded into the way more complex and way more powerful setting of feasible directions and tangent cones. In general, cones are very common if you go into the theory of optimization because they're a very useful tool to tackle constraint optimization or to tackle optimization problem in general. So if you're interested in getting more information or more insight into optimization, just Google feasible direction or tangent cones and you will end up with very useful results and a lot of books and papers. So this is a very, very interesting topic. Throughout the rest of this video, we will make use of the following function, which you can see here, which is called the projection function onto the closed and convex set A and B, which is just the interval, of course. If x is greater than b, well, cut it off and set it to b. If x is less than a, cut it off and set it a. And in the middle, so if x is in between a and b, just put it to be the identity. So keep this notation in mind. This is the projection function and we'll use this throughout the rest of this video. So assume that we want to minimize the following extended optimization problem. So here you can see we want to minimize f of x, but with an additional cost term, which reads as 1 over 1/2 times alpha times x squared. This is called the Tikhonov regularization of minimizing f of x, and the parameter alpha is called the Tikhonov regularization parameter. This is a very useful technique because if we add this very smooth and nice term here, we will increase our, let's call it this makes our problem much more nicer and tackleable by numerical methods, as you can see in a moment. And the hope is if we let alpha go to 0, that the solution of this Tikhonov regularized problem will converge to the unregularized problem. So this is just minimizing f of x. So this is just a remark. For now, let's assume we want to minimize this function here, which is called g of x. If we want to minimize g of x, we can apply our first order optimality condition, which we just have established, which reads as g prime x star x minus x star must be greater or equal to 0 for all x lying in the interval from a to b. However, we can compute g prime. G prime is just f prime plus alpha x. So there's nothing spectacular about this. And in the following, we will take a closer look at the variation inequality you can see here, and you will see that we get super nice results. So here you can see again the first order optimality condition, just as a reminder to keep it in, that you can take a look at this. And now we assume that the solution x star lies in the interior of our interval. So x star lies in the open interval from a to b. Then we obtain that x star is just minus 1 over alpha times f prime x star. And now you see where the thing is actually going. If now we have reformulate our optimality condition as a fixed point equation. And if you have a fixed point equation, you can hopefully tackle this with Newton. Let's take a quick look at the proof. The proof is quite simple. Assume that this is wrong. Then assume, again without loss of generality, that f prime x star plus alpha x star is greater than 0. Since x star lies in the interior of the interval, we can find an x bar lying also in the interval, such that x bar minus x star is less than 0. You make heavy use that x star lies in the interior, of course. But if we multiply x bar minus x star with our f prime plus alpha x star, we see immediately that this is less than 0. However, this is a contradiction to our first order optimality conditions because this term must be greater or equal than 0. So this shows that our lemma here is proven, and we know that for this case we obtain x star can be expressed as minus 1 over alpha times f prime x star. Now we go to the second case. Assume that x star is a. So now we are lying at the lower bound of our interval. Then we know that x star is actually a. Okay, this is true, but we also know that it is greater or equal than this expression we used before. The proof is quite the same. You can see it here. We find an x bar lying between a and b, since a is less than b, which gives us this inequality here, which has the first order optimality conditions. However, this gives us, if x bar minus a is greater than 0, this shows that f prime plus alpha x star must be greater or equal than 0. So just put it on the other side and you'll end up with our result here. So same, if x star is equal b, the proof is the same. We obtain that x star is less or equal than minus 1 over alpha times f prime x star. So what is this all about? We have now proven 3 lemmas, 1, 2, 3, and you can see it here. And if you take a very close look, then you see that x star actually can be expressed, or that the first order optimality conditions for x star can be rewritten to the following fixed point equation, which makes now use of the projection function. So x star is the projection on the set a to b, on the interval a to b, over minus 1 over alpha f prime x star. So this is an equivalent formulation of the first order optimality conditions. Just take the result of lemma 1, 2, and 3 and combine it all, and you see immediately that you will end up with this expression here. And you can see it here again, what I just told you, that the critical points, which are the points which are interesting, of the extended constraint optimization problem. So here we have again this Tikhonov regularization term here. This can be actually computed by solving the equation, the fixed point equation we just derived, which are equivalent to the first order optimality condition. This is something we can now tackle with our Newton method. However, just a small reminder, this is not true if alpha equals 0. If alpha equals 0, you can only prove such a fixed point equation if x star lies on the boundary. You cannot tell anything if x star is inside the interval. So just keep this in mind. This is a very nice result because this is something we can tackle. The numerical approach we want to follow is quite simple. We rewrite this fixed point equation as finding the zeros of the following function n. However, we cannot tackle this function directly by Newton because this thing is not differentiable, because we have some cuts in there. Any solution is, of course, well, Semismooth Newton method, which we haven't defined yet, but we are going to define this in the next minutes. So, to motivate the semismoothness, we start with the function f of x, which is just the maximum of x and 0. It's well known, or it's very simple to see, that this function is non-differentiable, because if you take a closer look at the point x equals 0, we get 2 different possible values for the limit. So either the gradient is 1, or the limit here is 1 if you go from the right side, or it is 0 if you approach x from if you approach 0 from the left side. So how do we deal with this issue that we have 2 different possible limits? Well, the idea is I cannot decide which is the correct limit, so let's put them all into one set. And to do so, we do this a little bit more general. We assume, or we define the set D index f, which contains all the points where f is differentiable. So going back to this maximum function, this would be the whole R without 0, because in 0 it is not differentiable. So a little bit more advanced here, because if you know that you have a locally Lipschitz function, you know that by the theorem of Rademacher that the function is differentiable almost everywhere. This means that the set R minus the points where f is differentiable has measure 0, in the sense of Lebesgue, of course. This, however, gives rise, or this motivates the following definition. We take all limit points, we take all points of our set df, where f is differentiable, and take all the limits, all the possible limits of the gradient, and put it into one set, which is called the Boulignon subdifferentiable, denoted, or the B subdifferentiable, which is denoted by partial B of f. It might look very complicated, but in fact it's just a notation. We will make this clearer in an example in the following slide. But we are not ready yet, because now this Boulignon, this B subdifferential set, this contains only of, or might contain only of distinct points. And this is something you do not want. This is something which hinders you to continue into extending your theory. So what we're going to do now is we define the set partial f, which is called the general gradient of f at the point x, to be the convex hull of the B subdifferential as at the point f. So the convex hull here is needed to formulate some product or the chain rule, because for the B subdifferential, this is, if you take a look at the proof or at the definition, you will see that this is technically not possible, but it is nice to have a convex set, because convex sets are very useful, especially in the optimization context. Okay, so let's do this as an example. Again, we take a look at our maximum function. If x is greater than 0, so if x greater than 0, we directly get that the B subdifferential contains only the point 1, because, well, it is differentiable, so all possible limits are 1. So this means the B subdifferential contains only 1. And the convex hull of a single point is, of course, the point itself. So the partial differential, the generalized gradient of f for x greater than 0 is just the set containing 1. So this is the big difference to the classical differentiability. The gradient is now a set. It is not a value, it is a set containing values. Similar, if x is less than 0, well, then the generalized gradient contains only 0. The fun starts when x is 0. In this, as we showed, we get that for the B subdifferentiable, we get two different possibilities. So we get 0 and 1, depending whether you go to the 0 from left or to the right. So now we are left with computing the convex hull of the set here, but this is quite easy, because well, the convex hull of 2 points is just the interval containing both points. So the generalized gradient of f at a point 0, well, it's just the interval from 0 to 1. So let's put it on one slide. We get for our function f, we get that the generalized gradient can be written in this form here. So we just proved this, or we just computed this. And again, similar, if you do it for the projection function, you get the following. You get 0 if x is less than a, or x is greater than b. So these are the points outside the interval. If you take a look at the boundary of this interval, well, you are left with the gradient, which you are left with the same calculation, and you see that you end up with the interval containing 1 and 0. If x is a or x is b. And on the inside, of course, the function is differentiable in the classical sense, leading to that the generalized gradient contains only the value of the gradient. So this is just 1. So now we have a nice formulation at hand where we deal with the non-differentiable points using limits and doing some closure and computing some convex hulls. I want to point out some remarks. I already said that it is important that we have a convex hull here, so that this means that the generalized gradient is always a convex set. This allows us to formulate some theorems which resemble the chain or the product rule for the classical differentiability. And furthermore, we know that if f is a local Lipschitz function, the general gradient A is always non-empty, meaning it exists, and it is convex by definition, and furthermore it is compact, which is if you go to the space Rn, it means it's bounded and closed, but you can generalize this in a little bit more, and this is a very strong result. Okay. There it is, the definition of semismoothness. We need a locally Lipschitz continuous function, then we call f semismooth at the point x if the following condition holds. Let's take a look at this monster. The right part here should be very familiar because this is the same as for classical definition of differentiability, for instance in the Fréchet differentiability. However, since the gradient or the generalized gradient is a set, we have to modify the limit here. So in the classical definition, we have a limit here. However, we cannot formulate this with a limit. We need a suprema because the generalized gradient here is a set. And even more, we do not compute the generalized gradient of f at the point x, but rather at the shifted point x plus d. Keep in mind that d goes to 0. If you are familiar with the Newton differentiability, there you use the same trick. And this trick is very helpful if you want to prove convergence or something like this. This is actually a very strong condition, but it can be shown that the function we're dealing with, or at least we have dealt with, so the maximum function and the projection function, they satisfy this property here, so they are semismooth functions. So we now can use the semismoothness and the generalized gradient we have defined to formulate a Newton method which actually can work, which can deal with functions which are non-differentiable in the classical sense. And the algorithm reads, as you can see here, we start with an arbitrary point. If next step is, if a suitable stopping criteria is satisfied, we stop the algorithm. This could be, for instance, that the gradient is close to 0 or something is close to 0. Just use the classical criteria. The interesting part is here in the point number 3. Instead of computing the gradient, which is not possible in general for our function f, we now take an element, and with an element I mean an arbitrarily chosen element from the generalized gradient of f at the point xk and compute the usual Newton iteration. And then repeat everything until you're happy. So the major difference is here by choosing another gradient or by redefining the gradient and using the generalized gradient as a suitable gradient replacement or something like this. So if you take a look closer, if you take a close look at this, you can ask yourself, okay, well, why do we need that f is semismooth? It is not needed here because semismoothness is based on the generalized gradient, not the other way around. So why is this algorithm called semismooth Newton method? And the answer is quite easy. You need this in the analysis. If you want to prove convergence or convergence speed of your Newton method, you need smoothness condition on your, or smoothness assumption on your function f. For instance, f should be twice differentiable or the whatever, to get quadratic convergence or something like this. So what we need is f to be semismooth because this resembles our smoothness properties. Furthermore, we assume that x star is a zero of our function f. Then we have two results. The first result is we have convergence or local convergence, meaning if our starting point x0 is close to or is close enough to the solution x star, we have a well-defined sequence by our semi-smooth Newton method. And further, and second, the sequence we are generating is converging to x star. And second, we know that the convergence rate is superlinear if all elements from the B subdifferentiable are non-zero. This, of course, number point 2, resembles the classical result you obtained from the classical Newton method. Okay, so this is this uses now everything we have established in this video. So we use the semismoothness and we use the generalized gradient to now have a method at hand which can deal with non-differentiable or with functions which are non-differentiable in the classical sense. And however, we still obtained convergence. So recall what we've started with. We started with minimizing the Tikhonov regularized problem, minimizing f plus some regularization term. And we showed this can be reformulated in finding the zeros of the following semi-smooth function. So all we have to do now is to find a suitable element from the generalized gradient for this combined function here. But this is quite easy because, well, just do the calculations. We know that a suitable element from the subgradient or from the generalized gradient looks like this. If we are at a point x equal a or x equal b, we just set it to be 0. On the other side, if x is inside the interval, well, we just do some chain rule here and end up with 1 over alpha times f prime prime x. So this here now this expression here can now be used to actually easily compute or actually implement the semi-smooth Newton method and get an algorithm for computing the solution of the constraint optimization problem. So this is now the end of the video. Let's do a short recap. What have we done? We have extended the classical definition of the differentiability to a wider class of functions using the B subgradient and the generalized gradient and the semismoothness. We have used this definition to define the semismooth Newton methods, and I also showed you, I didn't prove this, but I showed you some convergence result and convergence speed result. This method actually is quite used in the context of constraint optimization, mostly in the terms of Tikhonov regularization, and which is quite interesting. The concept of semismoothness and the semismooth Newton method can be extended to higher dimensions, of course. I have just showed you how to do it in 1 dimension, but the extension to higher dimension is quite straightforward. What is interesting, this function or the semismoothness can be extended to function spaces. So function spaces are, well, infinite dimensional spaces in quotation marks because it's a little bit more than this. But this concept of semismoothness is quite general. I know that this was a quite technical video, and I just scratched the surface, kind of the technical details I did not show you. So I heavily suggest you, if you're interested, look up the buzzwords I marked in red and get a good book on optimization and numerical methods, and well, get some more information about this. I hope you enjoyed this video. Well, see you around and have fun. Cheers.